We now represent some functions as power series as application of results in 11.8, so it will be interesting application. We will practice a little bit our mind. So just reminders, we know that a power series is actually a function. So when it's convergent, we can equate it to some explicit expression of a function, and that function is defined for all values of x that are in the interval of convergence of the series. So obviously this looks like a polynomial, except that this keeps going forever, so it's not really a polynomial. And again, this is a function of x is a variable, c0, c1, c3, c2, c5, those are the constants. So look, this looks like a polynomial, and this equality here holds when the series is convergent, and it's convergent inside the interval of convergence. Normally, to find the interval of convergence, we will use ratio test. Now, in this particular situation here, it will be actually simplified because we will use one generic series and then we will start modifying it a little bit and then playing with it. So basically things will be much simpler in our situation here. We remember our series of x to power n. So this is a geometric series. Obviously it's a power series, but it's also geometric. First term is 1 and the ratio is x. And we know for geometric series, the convergence, the condition is that the ratio in absolute value, so here absolute value of x, needs to be smaller than 1. So actually x needs to be between -1 and 1, and then we know that this geometric series is convergent. And we also know how to compute the sum of the geometric series. So it is the first term divided by 1 minus the ratio. Here the ratio is x. So this will be our series of reference for this section. Everything will start from this series and this equality here. Again, there are three pieces here. So the series itself, this geometric series, which is a power series, and the sum of the series, and the interval of convergence. So we have three pieces here: the series, the sum, and the interval of convergence, here between -1 and 1. So those are very important three things, and we will see them often in the applications now. So this series is convergent when x is between -1 and 1. Outside of that interval, series is divergent, so there is this equality is here true only for this interval. X is in this interval. Outside it's not true because the series is divergent. So what we realize is that the function here, that's a classical function. It is defined everywhere except at 1. So there's nothing particular about this function. What is important to realize is that this function is equal to this series only when x is between -1 and 1. Then we have equality of these two things. So those are two separate creatures, if we will, and then they coincide on the interval -1, 1. Outside of that, this series is divergent and it has nothing to do with the function. So the function exists normally without the series. Everybody lives its own life separately, but on the interval -1, 1, they are actually superposed. They are equal to each other. So just to realize, this is our function. So it's defined everywhere except at x equal 1. So this function is fine. What we realize is that the geometric series that we have here, our fetish series of x to power n, it is equal to this function on the interval -1, 1, excluding the -1 and 1, obviously. So for x is between -1 and 1, the geometric series is equal to this function. So that means this branch here represents the function between -1 and 1, and also it is a sum of the series itself. So the series lives for values of x between -1 and 1, and it's equal to this thing here. Outside of the interval -1 and 1, the series is divergent, so the, let's say, series doesn't even exist. But function is fine, so that's what we need to realize. The function and the series are equal only for certain values of x. They coincide in that short space. So series is one thing, function is another thing, but they superposed or they overlap, they coincide for certain values of x on a small interval. So that's what is interesting, and we will use this particular situation to create new series for new functions, basically starting with this geometric series and this sum on the interval -1, 1. So those are interesting things. Now we will exploit this further to create new different series for different functions and try to practice a little bit our mind. So again, on the interval -1, 1, the series is equal to the function. Just to note that at x equal 1, the function is not defined. Okay? Obviously, if I plug x equal 1 also, the series is divergent. At x equal -1, function doesn't have any issues, but the series will be -1 to power n, while the general term -1 to power n doesn't converge to 0, therefore the series is divergent also. So really, the equality is only on the open interval -1, 1. And we will start all of our exercises that are to come in this section from this equality here. So equality is valid only on the interval -1, 1. Just as illustration here, these are some partial sums of the series that show that more terms you add, closer you become to the function. Obviously, the function is the sum of the series, meaning you add infinitely many pieces of the series. Since this is a power function, power series, we know that we have some properties for the power series. So we have the interval of convergence that we find using the ratio test. So in this situation here for our fetish series, we already know the interval of convergence. We don't need to do any work for it. But what we learned in 11.8 is that power series can be integrated and differentiated term by term. And we will get another power series as a result. Now, the radius of convergence will be the same. The interval is practically the same. The only difference is sometimes one or both of the endpoints might belong to the interval or not. So essentially the interval is the same except maybe the endpoints. So that's very interesting because that's special property for power series. We can differentiate them as many times as we want, and we get a sequence of power series also, and the interval of convergence is pretty much the same except eventually the endpoints, but the radius is always the same. We can also integrate these power series term by term and get a new power series with the same interval of convergence except maybe the endpoints. So that's very interesting. So that's what we are going to do actually. We are going to practice using the integrals and derivatives of a power series. So here is just an illustration. So our power series is convergent to a certain interval and it's equal to a specific function. When we differentiate the function, is the same as differentiating the power series. So here you see C0 is a constant. If I take the derivative of C0 is 0, right? Because derivative of constant. Derivative of this term is C1. Here is 2C2 x minus a. And then the next term derivative will be 3C3 x minus a to power 2. So essentially this is what we have. Now to write it in a compact way, we observe a little bit what's happening. So this is x minus a here to power 0, right? So essentially what you can do is we need to write it this way, and then to write the generic term, you refer to this. The derivative of this term Cn is a constant. Derivative here is n goes down, and then the power is n minus 1. Derivative from inside is 1. So we had n goes down, so n Cn x minus a to power from n minus 1. Now what we realized is this series starts from 1, not from 0. That's why it is useful to write a couple of terms and differentiate just to see what's the beginning of the series. But usually when we differentiate, we will start, so here starts from 0, derivative starts from 1. If I differentiate again here, I'll have n Cn, and then this power will go down, so it will be times n minus 1, x minus a to power n minus 2, and we would start from n equal 2. So you can write it on your own just to see, but that's how it works in general. Also, we can integrate. So we can integrate this term by term. So integral of a constant. So we'll have C0 times x. Now here the writing is a little bit different just to have a generic term, because C0 times x minus C0 times a, that's a number, and we have constant of integration, so we can adjust that. Important thing is to remember our constant of integration. This will be crucial. In each integration we will have constant of integration, and we will try to find its value. Sometimes it will be 0, sometimes the value of the constant will be some number different from 0. So we need to be careful. Each time we integrate, we will have constant of integration. That's why I write it first, so we don't forget it. And then we just write the generic term. So you see here C0, the power here is 1. C1, the power is 2. C2, the power is 3. So Cn power n plus 1. Right? So downstairs you have 2, 3. So essentially if we go from here, if I integrate, I have x minus a, n plus 1 divided by n plus 1. So that's what we have here. And the constant. Again, constant of integration is super important. As we said, the radius of convergence is the same for derivatives, any number of derivatives, and any number of integrals. The interval of convergence will be pretty much the same, except eventually one or the other of the endpoints, and we need to examine the situation at the endpoints. We will see several examples of that. So the major result for power series is that we can differentiate each power series term by term. So the derivative of the series is equal to series of derivatives. And we can integrate term by term, which means integral of the series is equal to series of integrals. So we integrate the terms in x. We will see several examples of this. So this is our series of reference, our fetish series, geometric series, x to power n. So we will start with this series and we will modify it step by step. Eventually we will differentiate it or integrate or replace x by some expression. So that will be pretty much what we are going to do. Replace x by an expression everywhere. So we will replace it here, we replace it here, and we replace it here. We will be differentiating this term. That means we differentiate this. And also we can integrate the term, and then we integrate the term here. So that's what we are going to do essentially, and then have different variants of this. So let's say we want to find a power series for this expression here. Well, this looks like our fetish series, but instead of 1 minus x, we here have 1 plus x. So we know that our fetish series, this is geometric series, and its sum is 1 over 1 minus x for x between negative 1 and 1. So we will start from here. In order to have 1 plus x, I could replace here x by negative x. So it is a replacement strategy. So I have my reference series. Again, we need to memorize this series with the interval of convergence, super important. So now in order to get 1 divided by 1 plus x. So 1 plus x is 1 minus minus x. So now essentially what I'm doing is I'm replacing in this series x by minus x, and then I'm getting what I need. So I replace x by minus x here, this is what I get. And then if I replace x by minus x in this case, I'll have minus x to power n. So this is minus 1 to power n times x to power n. So this is our alternating version. So essentially, this will be our fundamental series, fetish series, and then this will be its cousin, alternating version of it. And again, here it is important to replace x by negative x everywhere. So here, in the term of the series and in the interval of convergence. So this series was convergent for x in absolute value smaller than 1. So we replace x by minus x. So we'll have absolute value of minus x smaller than 1. Okay, it's the same thing, but just to have a habit of replacing x everywhere. So we need to replace essentially x in 3 points, 3 locations, in the expression of the sum, in the expression of the series, and the third place is in the interval of convergence. So this is another variant. So we had our series 1 over 1 plus x. We found the expression. Now what we do is we multiply everything by x. So essentially we use the series that we just got previously, the alternating version of our reference series, and we multiply everything by x. So we essentially multiply every term by x. So as a result, we'll have this term times x, so x, second term times x, x squared, third term times x, x cubed, etc. So basically, what happens here is that we are multiplying by x everything. So if I multiply by x, essentially the power of x is increased from x to power n to x to power n plus 1. So that will be something that we will see often. If I need to multiply, I multiply everything. So essentially, I just increase the power of x. Another example, if I need to find a power series for this expression. So here this looks like our reference series, except here x is replaced by x squared. So that's simple. We will use our reference series, that's our starting point, with its interval of convergence. And then now, in order to get what we are asked, we simply replace x by x squared everywhere. So we replace x by x squared here, so we get our expression. We replace x by x squared in this term, so we'll have x squared to power n, so x to power 2n. And then we replace x by x squared in the interval of convergence, so we'll have x squared in absolute value smaller than 1. So again, x is between negative 1 and 1. So basically, it's straightforward replacement everywhere. In the sum of the series, in the expression of the series, and in the expression for the interval of convergence. Again, x squared in absolute value needs to be smaller than 1, so the values of x need to be between negative 1 and 1, so it's the same thing. Now this is just a little bit more evolved as an example. So we have 5 divided by 1 minus 4x squared. So the 5 will multiply everything, so that's not an issue at all. Now what we realize, our fetish series is 1 minus x. So here we will need to replace x by 4x squared. Now just 4x squared is 2x to power 2. It's very useful to write it that way. So essentially, I have 5 divided by 1 minus x, so it's 5 times my fetish series. And I need to replace now, in order to get this, x by 2x, everything to power 2. So instead of x, I'll write 2x to power 2. Right? So to power n, so that's what we get. And then the last piece I need to replace x by 2x, everything to power 2 in the absolute value here for the interval of convergence. So this is 4x squared, obviously, so that means that absolute value of x squared is smaller than 1 over 4, which means that absolute value of x is smaller than 1 over radical 4, so which is 1 over 2, which means x in absolute value is smaller than 1 over 2. So what we observe is that our fetish series, its interval of convergence is between -1 and 1, but for our new series, new function, the series is given here and its interval of convergence is between -1 over 2 and 1 over 2. That's why it is important to replace our expression here everywhere instead of x. So in the expression of the sum, in the expression of the general term of the series, and in the interval of convergence, in the expression for the interval of convergence. Super important. So what if I want to express this function as a sum of power series? Obviously, each time we need to keep our interval of convergence in place because the equality is valid only for x's inside the interval of convergence. Again, our starting point is always our fetish series. Now, we remember that 1 over 1 plus x is the same series but alternating version. So we can remember that or start from here and then go slowly. So in this situation, x needs to be replaced by -x squared, and then we will get what we need. -x squared here, so we have -x squared, everything to power n, and then in the expression for the interval of convergence, x is replaced by -x squared. We just do it systematically, automatically, we don't think too much. So here, -x squared, everything to power n, we have -1 to power n, and then x squared to power n, which is x to power 2n. Right? So this is what we get. Now, this expression here, again, it will be absolute value of x squared needs to be smaller than 1, so absolute value of x needs to be smaller than 1, so interval is still -1, 1. So that's what we have. R is -x squared. I just keep it formally because later on expressions will be different and more complicated, so it's important to just copy paste things properly and then work from this inequality here. Obviously x squared needs to be smaller than 1, so that means absolute value of x needs to be smaller than 1. So again, interval convergence is -1, 1 open. So those are some of the important things. When we replace x in our fetish series by an expression, we replace it in the expression of the sum of the series, in the general term of the series, and in the expression of the interval of convergence. So what is interesting is here we got this expression here in terms of power series. And then we realized, oh, if I integrate this, I get tan inverse. So why not find tan inverse as a sum of a power series and find the interval convergence? So since tan inverse is actually integral of our expression here, and that expression is equal to this power series on this interval, so we can integrate term by term, right? We could obviously integrate generic term, but I'm just expanding here a little bit so you see actually what's happening. So integral of 1 is x, integral of x squared, x3 over 3, etc. So here interval stays the same. We didn't replace x in this situation. Important thing is each time we integrate, we get a constant of integration. So that's why I write it first, so we don't forget it. We will need to find value for this constant of integration, obviously. So the generic term here for the series is this. Now this looks like a little bit complicated. So you see same power same denominator. Now, so how do I do this? Well, either I can construct from here, or simply I go here. Integral of this term is x to power 2n plus 1 divided by 2n plus 1. Now the only problem is, where do we start? So that's why I expanded a little bit, so you see what's happening. So normally when you integrate, you start with the same index n. When you differentiate, you lose 1. Each time you differentiate, you lose 1, so you will crank up here, but when you integrate, most of the time n stays the same. Obviously we can rewrite it later on, but just keep it as simple as possible. So for now, we use the property of the power series. Integral of a power series is a power series, and its interval of convergence is pretty much the same, except eventually the endpoints. And important thing, when we integrate, we have constant of integration, and we need to find a value for this one. So we know that tan inverse is equal to this expression here for any value of x between -1 and 1. So interval of convergence for now is -1, 1. Radius is 1, obviously. And we need to find value of x, of c, sorry, value of the constant. So that's important. That means this equality is true for any value of x between -1 and 1. So we could pick any value of x and plug it here and plug it here in order to find a number on this side equal to c plus another number here, so we can find the value of the constant. Now, we could take 0.2 minus 0.7, but the wisest thing is probably to take 0, because then if I plug 0 here, things simplify. So that's why we pick 0 as a wise choice, because then I evaluate tan inverse at 0 on one side, which is 0 obviously, and on the other side I have a constant plus, and then I replace x by 0 everywhere, so everything is 0. So essentially I have 0 equal constant plus 0, which means constant is 0. This is what will happen most of the time with tan inverse. We will have constant equals 0, but we still need to do the work properly. That means that finally the tan inverse is equal to this power series on the interval -1, 1. So now the only question is, what's happening at the end points? What's happening when x is equal to 1, and what's happening when x is equal to -1? So maybe these 2 points are included, maybe not, maybe one of them, I don't know, I need to check. Okay, now tan inverse is defined everywhere, so we don't have an issue. But if we have a function that is, let's say, not defined at x equal 1, there's no point of checking anything on x equal 1. But here, tan inverse is defined for all real numbers, so it is defined at -1 and at 1. So I need to actually check what's happening at both ends. How do I do that? Well, I plug x equal 1 and I check if the series is convergent, and then I plug x equal -1 and I check if the series is convergent. So if I plug x equal 1, I have tan inverse of 1, which is pi over 4, and in the series here I plug x equal 1, so I have 1 to power 2n plus 1, obviously it's 1. So I have on left side a number equal to this expression here, and this is an alternating series. By alternating series test, we can see quickly that this series is convergent. Similarly, when I have x minus 1, I plug -1 on both sides, so tan inverse of -1 is minus pi over 4, and on the left side, on the right side here, if I plug -1, I'll have -1 to power 2n plus 1, so it will be, so -1 to power 2n is 1, and then -1 to power 1, it will add here, so it will be -1 to power n plus 1. That's why we have n plus 1 here. So again, this is an alternating series. That's what matters at the end. It's just an alternating series, 1 over 2n plus 1. It is straightforward to show that this thing goes to 0, this expression here, and then it is decreasing. So the conditions for the alternating series test are very simple to verify. So that means that this series is also convergent. So it means that both of the endpoints, -1 and 1, are included in my interval of convergence because the series is convergent at those values. So now the interval of convergence for my series for tan inverse is -1, 1, inclusive of -1 and inclusive of 1. So that's why you have here smaller or equal. Just one observation here. You see pi over 4 is equal to this series here. So if I multiply both sides by 4, I have pi equal 4 times this series. So if you need to approximate pi, you can actually use this series here. You add first 10 terms, you get an approximation. You add first 20 terms, you get a better approximation. You add first 500 terms, you get a super good approximation of pi. So this is how you could actually approximate pi using a series. Just an observation. Here another example. The shape of the expression is not exactly what we are familiar with. Usually we have 1 divided by 1 plus or 1 minus something. Here is 2 plus x. Oops. We know what to do when we have 1 plus x or 1 minus x. But here we have 2, so what do? Well, we factor 2 downstairs. So we factor 2. So we have 1 plus x over 2. Now it's nice. We have 1 over 2, that's a constant, so we can multiply constant times the expression. So 1 plus x over 2, now we are able to do something with it. Obviously we can write it as minus minus, right? So now I have 1 over 2 that multiplies an expression. So I can find a series for this expression by using my fetish series and replacing x by negative x over 2. And then multiplying everything by 1 over 2. So that's very cute. So the series that I need to get, I will get it from my fetish series. So 1 over 2, I multiply everything by my fetish series. And now in my fetish series I replace, because here I have negative x over 2 instead of x, so I replace x by negative x over 2 everywhere. Here, so I get this part. Here, so I get negative x over 2 to power n. And also I replace it at the expression for the interval of convergence. Super important. We cannot forget it here. So minus x over 2 needs to be in absolute value smaller than 1. So my expression is equal to this thing here. So here I have negative 1 to power n, and then x to power n and 2 to power n. So this is again alternating series, it's cute. It is also a geometric series, so depending on how you write it, you will see one or the other. Now, what happens here? I have 1 over 2 multiplying the entire series, so every term of the series. And every term of the series has some power of 2 downstairs. So actually I'm multiplying every term by 1 over 2, so the 2 is multiplied downstairs for every term. So you see 2 times 2 to power n, you get 2 to power n plus 1. This is just a rewriting that looks cuter, but nothing special for that. If you leave it this way, it's fine, but I just wrote it in a compact way. You see 2 downstairs, so 2 to power n plus 1. Now, the interval of convergence, obviously I need to rewrite it a little bit so I get it properly. So common ratio is negative x over 2, and it needs to be in absolute value smaller than 1. So x over 2 in absolute value needs to be smaller than 1. So that means x in absolute value needs to be smaller than 2, which means x is between minus 2 and 2. So what we observe is that our fetish series is convergent between negative 1 and 1. Our new series here, for our new expression, is convergent between negative 2 and 2. Okay, that's cool. Now what happens at the end point, just to see. If I plug 2, I'll have here 2 to power n, so as a result here I'll have 1 over 2. So the general term doesn't go to 0 because it's a constant, and then alternating sign. So since the general term doesn't go to 0, series is divergent. At negative 2, similarly I'll get negative 1 over 2 and then the alternating sign. So the general term again of the series doesn't go to 0. Series is divergent by divergence test. So none of the points is included in interval of convergence. So that's why it stays open, minus 2, 2. So it's really important to replace the expression here everywhere. In the expression of the sum, in the expression of the general term, and in the expression of the interval of convergence. Super important. Another variant of this, so once we have our expression of the series here, we could actually multiply everything by x cubed for fun. So this new expression, how do I get the representation of this expression as power series? Well, I use my previous expression and I multiplied by x cubed. So x cubed multiplies the expression of the series. Now, x cubed does not depend on n. So this is series on n. So x cubed multiplies each term of the summation. So essentially, I multiply x cubed times x to power n. That's why I have x to power n plus 3. So this is something that will happen often. Whenever you multiply by a constant or you multiply by some expression of x, well, you can just move that expression of x inside here, the power, straight, and then adjust the power of x. So that's cute, nothing special there. Now, another trick that we have is integration and differentiation. So let's say we want to find the power series representation of this expression. Well, we again start always with our fetish series, which is convergent on the interval negative 1, 1, and this is the sum. What we realize is if we differentiate this expression here, we get this, because the derivative of this is negative 1 times minus x to power negative 2 times the derivative from inside, which is negative 1. So minus 1 times minus 1 is 1, so that's why we get this. So the derivative of this expression is this. But that's what we are looking for. Which means if I take the series for this expression and I differentiate it, I'll get exactly what I need. So I take my fetish series and I differentiate it and I get my expression. So I differentiate the fetish series. Simple, simple, simple. So derivative here is 0, then 1, 2x, 3x squared, 4x cubed, etc. So essentially we observe what we have here. It's 1, 2 to power 2x to power 1, 3x to power 2. So you see the 3, 2, 2, 1, and n minus 1, right? So nothing special there. Or also you could use the observation that when you differentiate this, you get n that goes down, x to power n minus 1. So that's what you have here. Now we started from 0, here we start from 1. It's useful to write it this way also just to see, or if you prefer, you can automatically differentiate this and adjust the n. So here it started from 0, here it will start from 1. If I differentiate again, n minus 1 will go down, I'll have x to power n minus 2, and here it will start from 2. What happens if I want to find the power series for ln 1 plus x? Well, if I differentiate it ln 1 plus x, I get this expression here. Well, I know already the series for this. This is the alternating version of our fetish series. So if I integrate this, I get ln 1 plus x. So derivative of ln 1 plus x is this expression here. Integral of this is ln 1 plus x. So essentially, I can use the alternating version of my fetish series and integrate it. Simple as that. So ln 1 plus x is integral of 1 over 1 plus x, obviously. So I can integrate my fetish series term by term. Here is just an illustration. Normally we will go faster, but this is just to show you term by term. So if I integrate, I have integral of this will be x, and then x squared over 2, then x cube over 3, etc. So basically just to see a little bit what's happening. When we integrate, we always have constant of integration. That's why I write it first so we don't forget it. So the term of the series, so 1 times x to power 1, x to power 2 divided by 2, x to power 3 divided by 3, x to power 4 divided by 4. So xn over n. And then you have alternating sign. You just adjust the power here. Again, we could simply integrate from here. We will get minus 1 to power n, and then x to power n plus 1 over n plus 1, starting from 0. So then when we adjust for the index, these things happen. So either you do it straightforward from here, or you expand a little bit and then you realize the pattern and you write it down with proper starting point. Now there are two things to do. First is to find the constant of integration. It is super important not to forget that. And then second thing is to see what's happening at the end points. So our interval is pretty much the same except maybe the end points. So those are the two things to check. First one is always to find the constant. Now we know that this equality is true for any value of x between negative 1 and 1. If we pick wisely, things will simplify. So if I pick x equals 0, summation here becomes very simple. I'm adding zeros. So that's wise. Most of the time we pick x equals 0 because it's wise. So I pick x equals 0 and plug it on left side and the right side. Correct? Because ln 1 plus x is equal to this expression on interval minus 1, 1. So if I evaluate it at x equals 0, I need to plug 0 here and 0 here. So that's what we do. ln 1 plus 0. Okay, so log 1 is 0. On the right side we have c plus, here instead of x we put 0, so basically we have 0 to power n now, starting from 1. So this will be 0 plus 0 plus 0 plus 0 plus 0. So I have a summation of zeros, which is 0. So I have on left side 0 equals c plus 0, which means c is 0. Often it will happen that c is 0, but not always. So we cannot just assume. We need to do the proper work. So now knowing that c is equal to 0, I can definitely write this equality here for interval negative 1, 1. Now the next step is to see what's happening at the endpoints. So let's examine the situation. Now first observation is at x equal negative 1, ln 1 plus x. If I replace x by negative 1, I have ln 0, which is not defined. Right? This equality needs to hold. For that to be true, this expression needs to be defined. So as a result, I need to get a number. And this part here needs to be convergent. So both of these conditions. At x equal negative 1, ln 0 is not defined. So that cannot be equality because one of the sides is not defined. So at x equal negative 1, the expression is not defined. So definitely x equal negative 1 is not in the interval where these two expressions are equal. Now let's examine the other endpoint, x equal 1. So I plug instead of x 1, so 1 plus 1 is ln 2. And on the other side here, I plug 1, simple. So I get this series. Obviously this is an alternating harmonic series. It's convergent, we know it, by alternating series test. So that means that the series is convergent at 1 and the function has the value and they are equal. Which means that this equality here holds, is true for all x's between negative 1 and 1, including 1, but not negative 1. So negative 1 open, 1 closed. So any x between negative 1 and 1, including 1, in those values of x, this equality here is true. ln 1 plus x is equal to this power series here. Just one observation, ln 2 is equal to this series, so alternating harmonic. So more terms here I add, closer I get to ln 2. So if I want to have an approximation of ln 2, I can add maybe 10 terms of this series and get an approximation. If I add 20 terms, I get a better approximation. If I add 100 terms, I get even a better approximation of ln 2. So you see my alternating series, we know that this alternating harmonic is convergent and it's converging to ln 2. So that's cute. Similar example, just instead of having 1 plus x, here is 1 minus x, so the derivative will have negative sign. So this is minus 1 times the expression. So we recognize that this will be replaced by our fetish series, everything multiplied by negative 1. So the negative 1 is outside, there is no n on it. It's just minus 1 times the entire series. So that's important. So now to get ln 1 minus x, we integrate that part. So negative 1 times the integral of the series. So we integrate term by term again. Integral of 1 is x, integral of x is x squared over 2, etc. And we don't forget the constant. So essentially we get our power series here. So x to power 1 over 1, x to power 2 over 2, x to power 3 over 3. So we see the pattern xn over n and starting from 1. So now our goal is to find c, and the next step will be to see what's happening at the endpoints. So again, to find c, we need to evaluate left side and the right side at any value of x between negative 1 and 1. And we need to choose something wise. So again, wise thing is to choose 0. It simplifies our life. So if we pick 0, we'll get ln 1, which is 0, equal to the right side. We'll have c plus summation of zeros, essentially. So c will be 0. But again, this needs to be done. We cannot just assume. We must do it. So now we know that our function ln 1 minus x is equal to this series with the minus 1 in front. And it's true for all values of x between negative 1 and 1. Now we want to see what's happening at the endpoints. Maybe one of them is included, maybe not, I don't know, let's see. So obviously at x equal 1, ln 1 minus x is not defined. So the equality cannot be true at x equal 1. Fine, so forget about x equal 1. Let's examine the situation at x equal minus 1. Well, 1 minus minus 1, so that's ln 2 again. And then in our expression of the series here, instead of x, I put minus 1. So I have alternating series. So harmonic alternating, we know it's a convergent series. By the way, we could take minus 1 times this, so it will be minus 1 and plus 1, but doesn't matter. We can keep it as is, doesn't change anything. So now what we realized is at x equal 1, the function is not defined, so the equality cannot be true. But at x equal negative 1, the function is equal to a number and the series is convergent. Therefore, at x equal minus 1, the equality is true. So our interval of convergence finally contains the negative 1. So it's between minus 1 and 1, but including negative 1. So close at negative 1 and open at 1. So that's why we have here smaller or equal. So you see this series here is equal to, this function here is equal to negative 1 times this series. So that's it. These are the options, replacing x by an expression in the expression of the sum, in the expression of the general term, and in the expression of the interval of convergence. Another option is taking derivatives or integrating. Whenever we integrate, we have constant of integration. We need to check the value of that constant by evaluating left side and right side at appropriate and wise choice of x. And then we check also the endpoints. Maybe one of them is included, maybe not, we don't know, we need to check it. So those are the options, essentially rewriting a little bit things so that they start looking like our fetish series, and practicing this a little bit as a intellectual exercise. So we need to solve some problems to get used to this, but that's essentially what it is. Our fetish series, we start from there, and then we try to figure out how we can rewrite the expression to fit what is asked from us.